Shut up. So next on Monday we have an exam. So exam 4. Monday, and then if you want to take it with the day class, that's Tuesday during the day. And the topics, there's only one topic, and that's circular motion. And then there is also going to be a quiz. So lecture quiz 3, that's also going to be on there. And that, to study the notes for that, just look at the notes where I'm talking about circular motion. And then the assignment, I still haven't posted, but here's the deal with the problem set. Instead of doing it as that like one-on-one checkout thing, you're just going to turn it in. So it'll be posted shortly. You'll just turn it in. And you're welcome to turn it in anytime before the end of finals week. I'd recommend getting it out of the way before then, but it's fine with me if it works out for your schedule. You have to turn it in by the end of finals week so I can get the grades in, but other than that, that's fine with me. So do definitely by the end of finals week. That's not really flexible because I have to turn in grades. If you want to turn it in after your grade is done, I guess you can. Any other questions about stuff coming up? Okay. And so we have exam 4 next week, and then that's Thanksgiving. And then I believe, is the makeup test the week after that? I think that might be right. 2 weeks after? Oh, okay. So yeah, so exam 4 on Monday. That's the week of Thanksgiving. Then there's a week after that, and the next week is the makeup exam. And then the next week is finals week. So everything's coming up now. So if you haven't learned any physics yet, it's time to start. And what are we talking about right now? Anyone remember without looking at notes? Yes, that's right. So we're talking about conservation of linear momentum. And remember, we break up conservation of linear momentum problems into 2 sort of subclasses. What are those? Yeah, very good. Inelastic and elastic. And which one means they stick together? Yes. So first, inelastic. That means the objects stick together. And this is the one that you hope for when you see a problem on a test or a problem set. This is the easy one. And it's easier because after the collisions, the 2 objects move as if they're a single object. So you only have one velocity variable you have to deal with after the collision. The other type is elastic. That's where the objects bounce apart. And this one, the physics isn't too hard. Like understanding what's going on, that's not too hard. but the math gets really messy. So I'm going to sort of, as we go through this, I'm going to try to kind of point out where the physics ends and where now we're just dealing with solving this math problem. And the good news is, you know, like I put a lot more emphasis on being able to do the physics than I do being able to solve the complicated math problem. So if you can get through setting up the equations the right way, you'll get the vast majority of points on these. And then, but I'll go through how to do the math too. So last time, I think we finished with a problem like this. It was an inelastic collision where there was a person on a skateboard cool pants. And there was a ball coming in at 15 meters per second. The ball had a mass of 0.4 kilograms. The person had a mass of 50 kilograms. And we were asked to find what's the speed, or really it was the velocity. What's the velocity vector of the ball-person combo after the catch? And the answer was, in the x direction, 0.119 meters per second, nothing in the y direction. So the velocity after the collision, after the catch, was a lot closer to the velocity of the person before the catch than it was to the velocity of the ball before the catch. And why was that? Yeah, because the mass of the ball is small, the mass of the person is big. So now we're going to do the same problem. Oh no, before we do that, I have to tell you about elastic. So now I'm going to talk about elastic collisions, give you a set of steps you can follow to do elastic problems. And once I'm done with that, we're going to do this same problem again, but assume that the ball bounces off of the person. So instead of catching it, it bounces off his hands. So the ball bounces one direction, the person rolls the other direction. Anybody have a sense of, so we know that after this person catches the ball, his speed is 0.119 meters per second. Do you have an intuitive sense of what his velocity will be after the ball bounces off of him? Is it going to be faster or slower? Slower? Wrong. And I'm not even going to tell you what the answer is. And the way, it is faster, very good. He is going to be going faster. Here's how you can tell. Here's sort of an explanation of why it is. If you think of it as, so your momentum is a vector property. And so the momentum before the collision is this momentum of the ball plus this momentum of the person, 0, right? These add up to a total momentum like this, right? After the collision, in the inelastic case, they're going, you know, the ball has this momentum, the man has this momentum, and they add up to say that the momentums have to be the same before and after. Right? This is inelastic. In the elastic case, the ball actually has a momentum this way after the collision, right? It might not be that much, but it's going in the other direction. And so the momentum of the person has to make up for the fact that the ball's momentum is in the other direction. So it has to be extra long in order for them to add up to be this. Okay, so now we're going to talk about elastic. So this is when objects bounce apart. And they bounce apart in such a way that the total kinetic energy before the collision equals the total kinetic energy after the collision. So we don't know what kinetic energy is. So we're going to have to deal with that. So here's kinetic energy. An object with mass m and speed capital V has kinetic energy of 1/2 times the mass times the speed squared. So if you're trying to have an intuitive sense of what kinetic energy is, something that's big and fast has a lot of kinetic energy. Something that's small and slow has little kinetic energy. So, you know, a train has a lot of kinetic energy. A snail has not very much kinetic energy. Brakes, like what your brakes are doing when you stop your car, is they're stripping kinetic energy away. They're turning that energy into heat, maybe a little bit of light, and that energy is being taken away from your car, you know. If you know an object's velocity vector instead of its speed, remember that for any vector, the magnitude of the vector is the square root of the sum of the squares. That's a Pythagorean theorem thing. And so the speed is always equal to the square of the x component of velocity plus the square of the y component of velocity square root. So you can also write, using this idea, you can also write the kinetic energy as 1/2 times the mass times the x component squared plus the y component squared. SI units. This is actually the first time in this class that we've talked about energy at all. All types of energy have the same kind of units. Based on this equation, this expression for kinetic energy, you can see that the units have to be kilograms, meters squared per second squared. Yep.
For that second kinetic energy equation,
Yeah.
it would be Vx squared plus Vy squared all of that squared.
Well, it's a square root. So then when you square them, you get rid of the square root. You know what I mean? V is the square root of those two things. And so V squared is just Vx squared plus Vy squared. So SI units for energy are kilograms, meters squared per second squared. Another way you can think of that is, remember, kilogram meters per second squared is a Newton. So you can also think of this as newtons times meters. And this idea of energy, I mean, it's a hugely important topic in any kind of science. And so people give this unit its own name, which is the joule. And you abbreviate it capital J. In an elastic collision, kinetic energy is conserved. You can think of that as the definition of an elastic collision. So remember, elastic means shape returns, right, when you remove the force. So if you think of like a super ball, you think of that as like an elastic object, okay, like a rubber ball. So if you slam two rubber balls together, they smush, and then they spring back to their original shape, and they bounce apart because of that springing back to their original shape. And so the fact that this kinetic energy, or essentially the speeds of these objects, some sort of a total speed is conserved, comes from the fact that these objects bounce back into their original shapes. Okay. The kinetic energy is conserved. That means 1/2 times the first mass times its speed squared plus 1/2 times the second mass times its speed squared before the collision is equal to 1/2 times the first mass times its speed squared plus 1/2 times the second mass times its speed squared after the collision. And so the mathematical messiness of these elastic problems comes from the fact that we'll have to solve a system of two equations now. Those equations are conservation of linear momentum and then conservation of kinetic energy, Koch. And so how is it that we only had to solve one equation for the inelastic case, and we have to solve two equations for the elastic case? That doesn't seem right to me. So, like, if you have more equations, you must be getting more out of it, right? I mean, you have to have the same number of variables as you have equations. That's just common sense. So, like, what's the extra variable that you're having to deal with in an elastic case? How is it that you have fewer variables to solve for inelastic problems than elastic problems? It comes from sort of the definition of what happens in elastic collision. Yep. Yeah, exactly. Two separate velocities is usually what we're solving for. Like, so in an inelastic collision, these two things move together. We only have to solve for one velocity because they have the same velocity. In an elastic collision, they bounce in different directions. We have to solve for those two different velocities. And that's why we need two equations to solve for it. Okay. So here's a general method you can use for elastic collisions. And I should say, we're only going to be doing sort of one specific type of elastic collision. So I'm going to say this is a method you can always use in this class, but there are other types that we're just not dealing with. The first step is choose a coordinate system. And remember, we're always doing this in a top view. That's the same as in elastic. And you're going to choose your coordinate system with the x-axis parallel to the motion. Well, what if our problem has two objects coming in at different angles? They'll bounce and leave at different angles. So which of those four directions is our x-axis going to point in? The answer is, in this class, we're not dealing with that case. We're only dealing with the cases where all motion takes place in a line. Okay? So notice we'll only do elastic problems with all motion before and after the collision along a line. So if you think of it in terms of pool, pool is all about collisions, and conservation of momentum is a sort of a natural thing to use if you're calculating collisions in a game of pool. We're going to be able to do like problems where you're shooting straight at a ball, one ball hits directly into the other one, and they stay along a line. But the idea of pool is, most of the time you don't have exactly straight shots. You're trying to get them to angle by getting them to bounce off in different directions. We can't deal with those problems in this class. There are ways to do it. We're just not going into that. Okay. Second step. The x component of conservation of linear momentum gives the first equation. So for example, our first equation of our system of two equations we're going to use says m1 v1x plus m2 v2x before the collision is equal to m1 v1x plus m2 v2x after the collision. Three, use the conservation of kinetic energy for the second equation. So once you do that, you have two equations for two variables. Those two variables are usually going to be v1x and v2x after the collision. So these three steps, this is all the physics, okay? The fourth step is the one that takes more than half the time of the problem, and in a 6-point problem is only worth 1 out of the 6 points. Okay, so these first three steps, those are 5 out of 6 points. You could stop right there and get a B on the problem. The tedious stuff now is step 4, and to do that, you're going to substitute the first equation into the second equation and solve. And the reason this gets so messy, like problems, most of the problems that you've probably done in math classes and in this class, when you substitute one equation into another equation, it's not that horribly messy. The problem here comes from the fact that the second equation has the variable squared, okay? So you're going to have to use FOIL to multiply out this binomial expression. And then you're going to have to use the quadratic formula to solve this thing after you simplify it. It just gets to be a real mess, okay? But that's how it is. Does anyone have any questions so far? So I think these steps are going to make a lot more sense once I go through an example problem. But anything occurred to anybody about this yet? Okay. So I'm going to go through these steps with the same example problem we did, but this time so we still have the skateboard. We still have the person on the skateboard, but this time, instead of catching the ball bounces off of him. So what's the person's velocity vector after an elastic collision? And again, the ball is coming in at 15 meters per second. So the only difference is he doesn't catch it this time. It bounces off of him elastically. The ball has a mass, same mass it did before, 0.4 kilograms. and the person has the same mass as before, 50 kilograms. And so what did I say? Is his speed gonna be greater or smaller than it was in the inelastic case? It's gonna be greater, yep. So remember, we're always going to do these problems in a top view. So it looks something like this. Before the collision, the ball has a velocity of 15 meters per second. Well, it has a speed in this direction. So now, how do we want to orient the coordinate system? Yeah, in the direction of motion. All the motion is going to take place along this line. After the collision, the ball's going to bounce. If it bounces back in this direction, it's going to bounce back along the same line. So you really have two choices, and it doesn't matter which you choose. In this case, I don't think very many people would choose the upside down coordinate system, but you could. But what you need to do is put the x-axis along this line. So the first equation comes from the x component of conservation of linear momentum. So before the collision, we have the mass of the ball times its velocity. What's its velocity before the collision? Yeah, positive 15. Plus the mass of the person times his velocity before the collision, 0. And that's equal to, we'll just add up the two masses. Oh no, I'm going back in time. This is elastic, so the mass of the ball times its velocity after. I'll call that V1. Plus the mass of the person times his velocity after. I'll call that V2. Okay, so if I simplify this, 0.4 times 15 is 6. 6 is equal to 0.4 V1 plus 50 V2. So that's our first equation. And now we have to get the second equation. The second equation comes from conservation of kinetic energy. So 1/2, before the collision, we have 1/2 times the mass of the ball times the speed squared. You can always just, in these problems, the speed, you can always just use the variable representing it. Well, this is before the collision. So before the collision, the speed is 15 squared. The kinetic energy of the person is 1/2 times the mass of 50 times 0 squared. After the collision, the kinetic energy of the ball is 1/2 times 0.4 times the variable representing the velocity after the collision squared. Plus 1/2 times the mass of the person times his velocity squared. And if you simplify that, you get 45 is equal to 0.2 v1 squared plus 25 v2 squared. That's equation 2. Okay, so that stuff isn't too confusing yet, right? I mean, we defined these variables that represent the velocity after the collision, and we have a system of 2 equations in terms of those variables. And if you can get to this point, like I said, that's 5 out of 6 points on the problem, and even if you don't do any more. And I just want to be clear about that, like you can sort of ground yourself on that. Like that's the end of the physics, but because now things are going to get really ugly. Okay. So now conceptually what we're doing is easy. We're just taking equation 1, expressing, say, v1 in terms of the other stuff, and then substituting that into equation 2. But in practice, you're going to see where it goes. So now we're going to substitute 1 into 2. I'm going to rewrite equation 1. So v1, well, let me do it in 2 steps. So 0.4 v1 is equal to 6 minus 50 v2. I just rearranged equation 1. And now I'm going to divide both sides by 0.4. So you get v1 is equal to 15 minus 125 v2. So that, I'll write that, since that hasn't added any new information to equation 1, it's just rearranging stuff. I'll call that equation 1b. Okay. It's equivalent to equation 1, but rearranged. But v1 doesn't appear by itself in equation 2, so we can't really substitute it yet. Okay? So to substitute, we have to square this. We have to square both sides of this equation. And so v1 squared is equal to 15 minus 125 v2 squared, which means multiply by another 15 minus 125 v2. And to multiply that out, we have to use FOIL. Remember that, first outside, inside, last. So v1 squared is equal to, so the first, multiply the first, you get 225. Outside is 15 times negative 125 v2. So that's minus 1875 v2. Inside, you're multiplying these two. So that's minus another 1875 v2. And then last gives you plus 15,625 v2 squared. And then simplify a little bit. You can combine those two middle terms and you get 225 minus 3750 v2 plus 15,625 v2 squared. Okay. Again, this is just another way of writing equation 1. So I'm going to call this equation 1c. But now this is what we're going to substitute into equation 2. So all of this stuff on the right side, we can replace, in equation 2, we can replace the v1 squared with that. Okay. So let's see. So put equation 1c into equation 2, and you get 45 is equal to 0.2 times all of this stuff, 225 minus 3750 V2 plus 15,625 V2 squared. And then plus the rest of equation 2, which is 25 V2 squared. And now you have to distribute the 0.2 through. And you get 45. Can someone help me multiply this? I don't have this step written down. But 45 is equal to, I know this one's 45. This one is, okay, minus 750. Plus 3125 V2 squared plus another 25 V2 squared. So I'll just make this 3150 V2 squared. The 45s cancel, and you end up with 0 equal to negative 750 V2 plus 3150 V2 squared. And I believe, well, okay, so how do we solve this? I mean, now we have what our goal was. We have one equation with only a single variable in there. How do we solve this? Yeah, that's what I would do. I mean, that way you can just always do this the same way. In this case, it's not too hard to factor it, but if you're looking for a way to simplify the steps, do it the same way every time. Just use quadratic formula. This is A, this is B, and so you get V2 is equal to 0 or 0.238 meters per second. Now, this is something you're going to always see when you do the quadratic formula. You know you're always going to get two roots. So what do the two roots mean? Well, one of those roots is always going to be the speed of the object before the collision, and one's going to be the answer you're looking for. In our case, this was the, I said speed, it's really velocity, but this was the velocity before the collision. So we're going to reject that one. And that means this is the answer. And so after the collision, the person's velocity is 0.238 meters per second. That's twice as fast as the person's velocity when he caught the ball. Any questions about that? So then you just take this solution for V2 and plug it into any one of these, plug it into the simplest equation you have. You know, you could plug it into equation 2, but that's unnecessarily complicated. So plug it into one of the versions of equation 1 that you have. solve for V1. And I guess let's do that. So plug it into 1b here, and you get, what's 15 minus 125 times 2.238? Okay, so the ball's velocity, the ball's velocity after the collision is negative 14.7 something, 5, which means basically the ball just acts like it hit a brick wall. It bounces back with almost the same speed in the opposite direction, and the person goes this way. So I want to ask a couple of intuitive questions. What would happen if instead, so in this case, the ball was lighter, the person was heavier, the ball hit the person, and they went in opposite directions. What relationship between those masses would you need for them both to go in the same direction that the ball was initially going?
Similar masses?
Actually, it could be similar, but it's any time if the ball was heavier than the person, they would both keep going in the same direction. Okay? So what does that suggest you would need for the ball to stop dead and the person to take off in the direction the ball was going? Equal masses. Yep. And so that's the next problem I want to do. Not with the ball though. So it's going to be cool because I'm going to say a different word than ball and person and put different numbers in it. Any other questions about this example before I go on?
So then, I mean, so it was going 15 meters per second before, but then it pretty much transferred to 0.25 almost towards the person and then back at 14.
Well, it transferred more than that into the person. It transferred 15 plus 14.75 into the person. You know what I mean? Because it switched directions.
Can the velocity overcome smaller masses? Like, I mean, like a bullet? You know?
Yeah. Uh-huh.
You know, it hits something that's flying back.
Yes.
You know?
Right.
Okay.
So yeah, just depending on what the velocity is, a light thing can make something go very fast, you know.
A beach ball moving at 200,000 miles an hour.
Yeah, right. It's hard to get that to, because there's a lot of air resistance.
Yeah.
But yeah. So the next example is, so think of, you know, that executive desk toy that they used to sell at like Sharper Image and stuff. I think Sharper Image might not be around anymore, so I don't know if anyone makes these anymore. But the idea is that you pull the ball on one side out, let it go. It comes in with a speed v. When it hits these, the three in the middle look like they don't move at all. They stay exactly still in the middle. The one coming in from the side stops dead. So you still have 4 that are stopped like this. And the one on the other side leaves this way with a speed v. Okay. We're going to we'll do the rinky-dink version. We could do this, it would just take a lot of time because we have to deal with ball after ball after ball along this string. So we're going to do the like assembly line worker desk toy, you know, rather not the executive. So it's just going to be like this. It's going to come in with a speed V. And then this one's going to stop dead, and this one's going to leave with a speed V. So our top view, we have one ball coming in with, we should probably just give it a speed. Let's say 4 meters per second. That's a little fast. Let's say 2. And let's say the mass of each of these balls is 0.1 kilograms. And how do we know that these both have to be the same mass? Because I just said that like 2 seconds ago. So if this one was, yeah, to get this one to stop dead, they have to be the same mass. If the one initially moving had a bigger mass, then they would both, after the collision, be moving to the right. If the one that initially has a velocity had a smaller mass, then that one would hit this one and bounce this way, and the other one would bounce the other way, like the example we just did. Okay, so what direction, how do we want the coordinate system? So X that way, then Y has to be that way. Conservation of linear momentum, X components says 0.1 times 2 plus 0.1 times 0 is equal to 0.1 V1 plus 0.2 V2. Rearrange that and you get 0.2 is equal to 0.1 V1. I didn't rearrange anything. I'm going to. What the? Okay, so 0.1 V1 is equal to 0.2 minus, oh, and sorry, I messed something up here. This 0.2, that should be the mass of mass 2, so that should be another 0.1. So if you rearrange that, you get 0.1 V1 is equal to 0.2 minus 0.1 V2. And then multiply everything by 10 and you get V1 is equal to 2 minus V2. So that's like our equation 1B. And now we can go to the kinetic energy equation. Before the collision, we have 1/2 times 0.1 times 2 squared plus 1/2 times 0.1 times 0 squared is equal to 1/2 times 0.1 times V1 squared plus 1/2 times 0.1 times V2 squared. And so this gives you 4 times 0.05. That's 0.2, right? And that's equal to 0.05 V1 squared plus 0.05 V2 squared. That's equation 2. Okay, so let's take a couple minutes and see if you can work through this substitution. You're going to take that equation 1b and substitute it into equation 2.